Homework sheet U11d question 4. We've got quite a lot of information in this question before we can start to approach it. Liquid is pouring into a large vertical circular cylinder at a constant rate of 1600 centimeters cubed per second. The units in that sentence give us our rate of change variables, volume over time. So this is our construction of dV dt. 1600 cubic centimeters per second going in. But it is also leaking out of a hole in the base at a rate proportional to the square root of the height. So if we've gone for a positive rate of change for liquid going in, we need to take away any that is coming out. We need a constant to represent our proportion. I would normally use k, but as k is coming up a bit later on in the question, I'm actually going to use a different variable, lambda. And it was proportional to the square root of the height, so lambda times root h. In this question we need to get to dh dt, so we need some way of connecting dv dt to dh dt. We are also told that the area of the cross-section of the cylinder is 4,000 centimeters squared. The cylinder is pi r squared h. If the area is 4,000, then our volume is 4,000 h. That's helpful because we can now find what dV dh is, which is just 4,000 by differentiating. Our rate of change can be connected up using the chain rule. We need to find dh dt. That is dh dv times dv dt. If we imagine that these are fractions, the two dv's can cancel each other out and we're left with the dh dt on either side that we need. They're not actually fractions, but we can pretend that they are for this purpose. dh dv is 1 over dv dh, so that is 1 over 4,000. And our dv dt we found earlier is 1600 minus lambda root h. We can work out what 1600 over 4,000 is, which is 0.4. And if lambda is a constant, when we divide it by 4,000, we're going to get another constant. That constant I'm going to call k times by root h, where k is equal to lambda over 4,000. In part B, we're given a bit more information that when h is equal to 25, water is leaking out of the hole at 400 centimeters cubed per second. If we look at the units, the centimeters cubed per second means that we're dealing with the dV dt equation, not the dh dt. And we're just dealing with the negative part of our dV dt equation. So minus lambda lots of root 25 is equal to 400, or minus 400 because it's the liquid that is leaving. If k was equal to lambda over 4,000, then lambda is equal to 4,000 k. I can remove the minus from both sides, so I get 5 times 4,000 k is equal to 400. That's 20,000 k is equal to 400, and if I do the division, k is equal to 0.02 as required. In part C, we're asked to separate the variables of our differential equation. To do that, we need to move all our h terms to the left-hand side, any t terms that we were to have to the right-hand side, and then we can integrate both sides. Now we have to treat the entire right-hand side as a single term because it's all added and subtracted to each other. We can only multiply and divide to separate a differential equation. So I have to divide the left-hand side by 0.4 minus 0.02 root h. And keep my dh over on that side. If I've divided the right hand side by that term, I'm left just with 1, and I can also move my dt up to the right hand side as well and integrate both sides. Now we're going to have limits for our left hand side because we're doing it between 0 and 100 to go from an empty height to a full height of 100. We don't have any limits for our right hand side, however. The right hand side just integrates to t. I'm going to swap my left and my right hand sides over. And then we need to multiply up the left hand side by a constant to get to the one that's required. First thing I'm going to do is I'm going to take out a factor of 0.02 on my denominator. That gives me 20 minus root h, which is looking more like what's required. And so if I just multiply top and bottom by 50, that will get rid of the 0.02 on the top and give me the 50 on the top that is required. In part D, we're given a substitution to allow us to solve this integral. The first thing you should do when you're given a substitution is differentiate it, and we can find dh dx. This is an application of the chain rule. We're going to get two lots of the bracket to the power 1, and we're going to have to times that by the differential of the bracket, which is minus 1. With a little bit of rearrangement, I can separate up my dh dx, and I can expand the bracket to get dh is equal to minus 40 plus 2x lots of dx. I can use this when I make the substitution now. I'm still going to have a 50 on the top of my differential. I'm now going to get 20 minus root h. Root h is just going to be 20 minus x, so that's 20 minus 20 minus minus x. And I can replace the dh with the 2x minus 40 lots of dx. My expression is now entirely in terms of x, but I haven't changed my limits yet. When h equals 0, I need my bracket to be 0, and that gives me x equals 20. When h is equal to 10, when h is equal to 100, I need my bracket to be equal to 10, so that gives me x equals 10. Now what this means is that my limits appear to have swapped over. My bigger number to start with was on the top, and I'm going to replace that with a smaller number on the top. And when h is 0, x equals 20. Now when I come to simplifying this, I can swap my limits over if I multiply the entire expression by minus 1. So I can now put my 20 on the top and my 10 on the bottom. And when I expand my brackets, if I times by minus 1, I'm now going to have 40 times 50 to get me 2000. And I'm going to get 50 times minus 2x to get me minus 100x. And if I simplify my denominator, I'm just going to get an x on the bottom. To actually perform this integration, I want to separate up my fraction into two fractions. So I want to integrate 2000 over x minus 100. The integral of 2000 over x is 2000 log x. The integral of minus 100 is minus 100x, and that's between 20 and 10. If I plug my limits in to this equation, I'm going to get 2000 log 20 minus 2000 minus 2000 log 10 plus 1000. And if I simplify these, I can take the 2000 out as a common factor and get log 20 over 10 using log laws to get 2000 log 2, and minus 2000 plus 1000 is minus 1000. Part D asked us to find the exact value, and so that's where I'm going to have to leave it. In part E, we're asked to find it as a time, giving our answer in minutes and seconds to the nearest second, so I need to type that into a calculator. T is equal to 386.29 seconds. And so if I work out how many lots of 60 that gives me, and what I have as a remainder, that gives me 6 minutes and 26 seconds to the nearest second.